Hey, good afternoon. I'm Samir, an AI/ML solutions architect at AWS or Amazon Web Services. And so this talk is about the concept of machine learning at the edge. And I will talk a little bit about this concept. And also I brought some use cases or real stories of customers that are using the infrastructure and adopting our services to build machine learning at the edge solutions. Okay, but what is machine learning at the edge? So this is a buzzword, basically, and it's a concept that describes, so when you get a trained model, it can be trained on the cloud or on premises in your laptop, and deploy this model to an edge device. An edge device is basically a hardware device outside the cloud, outside a big data center. So, and there is a confusion about this concept that some people think that it's just IoT. So machine learning at the edge doesn't depend on IoT. So IoT is normally about the application life cycle, or how to create an application, deploy to an edge device, and just collect data from some source and send to the cloud or to an on-prem data center. So, but you can enrich an IoT application with machine learning at the edge and create a more sophisticated application. Okay, so machine learning at the edge is basically about the machine learning life cycle. And just to give an idea, so you can have like the machine life cycle starting on the cloud side. So a data scientist will use the tooling to explore the data, prepare the data set, train your model, and then eventually you need to compile this model or optimize this model for edge devices, because this is an experimental area and normally the edge devices are way limited than the devices you have on the cloud. And then finally, after compiling the model, you can deploy this model to multiple edge devices. So a mobile phone is an edge device. Just to give an idea, so when you create an application or a mobile application, you normally publish this application to Google Play or Apple Store. But if you decouple the machine learning lifecycle from the application lifecycle, you increase the power of the application, the final solution, because you can deploy the application once and then keep evolving the model. So you can train and retrain the model and keep deploying the model to the edge application without changing the application itself. Okay. And then what is this edge device that will run and accelerate the machine learning model? So this is like a proposal of a classification of the edge devices based on the distance from the cloud or from a big data center. So how far the edge device is from these environments. And of course, many customers, especially the industrial manufacturing customers, they have places, warehouses, factories, and in these places you have some certain of good or reliable connectivity, or eventually you have some local data centers, bare metal, virtual machines that you can run more complex or more powerful models and applications. So this is normally the start of the edge, and that's why I said that you don't need IoT. For many of these customers, they are just using Docker containers deployed to x86, 64 machines, bare metal, and running the models on CPUs or GPUs. Okay, and also the connectivity and the power source, it has some good level of reliability. And when you start going far from the cloud or from big data centers, you can see the second column. So we're calling it near edge. You have still scenarios like inside a city where you have 5G or good connectivity, but you have mobile devices that rely on battery, and and here we start having some restrictions in terms of computing power to run these machine learning models, to accelerate the machine learning models and also save energy. And the extreme scenario is far edge, so agriculture, mining, or eventually some surveillance cameras that can never stop working, even without connectivity or with low energy. And then in this scenario, you have lots of other restrictions, and the edge device needs to have capabilities to store data when there is no connectivity, to save models. And in this scenario, you also need to apply extreme model optimization to reduce the size of the model and make them run on small microcontrollers or small simple CPUs. And of course, it limits the models that you can run on these devices, but it is a good solution depending on the scenario. Okay, so with machine learning at the edge, you can do a lot of things, not only in the industrial, the manufacturing, but also healthcare, predictive maintenance, security, and other areas. So there are many areas that can benefit of machine learning at the edge. But this is a very experimental area, and when you start working on optimization, sometimes this is an activity that requires a lot of effort, and so experts in these devices, these CPUs, and to hack the model sometimes, to change the architecture of the machine learning models, especially when you work with computer vision at the edge. So many challenges, especially when you work with just one place. So let's say you have one factory, and there you deploy your machine learning models, and then you start rolling out the solution across multiple factories around the globe, and then in the end you have a fleet of devices, hundreds of devices, maybe thousands or millions of devices, and then you have this concept of fleet of devices. And there is this concept of machine learning ops or machine learning automation, which is necessary for these cases. And in an extreme scenario like this, you will start the automation on the cloud side or on-prem, and then you will continue this process throughout the edge and up to the edge devices. Okay, and there you can also control the life cycle of the machine learning models and things related to monitoring, improving the model performance, A/B tests, and other things. So let's talk about one real story. So this is a use case related to defect detection that I'm working with one of our customers, and they have a product. And this is a public data set, by the way. This is not the original data set, but it is similar to the original data set used by the customer. So you have a conveyor belt and a camera installed on top of the conveyor belt where the products they pass. And it takes pictures of the surface of the object. So in the first row, you can see the picture of the surface, and these artifacts there in the images are just scratches, risks on the surface. And this is what this customer wanted to detect. The second line, the second row, is the ground truth, or the labeled data set for semantic segmentation. So because in this case, they don't not only want to classify if the product has a defect or not, but also identify the place or the area of the defect, and also return a blurb of the pixels corresponding to the area of the defect. So the second and the fourth row are the same, and the last two rows are just good products without defects. Okay, so, and this is the reference architecture of this solution. So at the left side, you can see the automated environment, so with machine learning ops, integrated with CI/CD. So there, a data scientist created the model, optimized the hyperparameters, and prepared the solution. And then, using this, there is an automated machine learning pipeline that does data preparation, model training, and then optimize the model for the edge device. And at the right side, you can see the edge location, or the factory in this case. The edge device here is just a bare metal, an x86-64 machine, an Intel machine. And there's no, and they are just deploying the whole solution using Docker containers. So you can see SageMaker Edge Agent, which is an agent, an extension of the service, the SageMaker, which is the service provided by AWS for the data scientists to prepare the models, to train, to do everything related to machine learning. But also you can deploy this Edge agent, which is a daemon or a Linux or a Windows application that runs in background. So it loads the models optimized for that device and exposes as an API for the application. And then there, so in this case, it is getting the predictions or getting the masks, the defects, and then shares this information with the application, and there's a business logic there classifying the issues in this in a state machine that decides if it's necessary to send a message to the worker or stop the production or run any local procedure. Okay. So this is important, especially when you have a heterogeneous fleet of devices. So this is just a feature they use called SageMaker Neo, which is a feature of SageMaker, but it's based on an open source tool called TVM, Apache TVM. It's an extension of TVM because it also integrates with specific toolkits. So it basically translates the original model. So this model was trained using TensorFlow, the UNet semantic segmentation, and it doesn't matter which one of these frameworks the customers are using, you can translate this model and optimize for a combination of target platforms. This is important if you have a heterogeneous fleet of devices, because you don't need to worry about the specificities of the hardware. So for instance, they are also experimenting with Umbrella CV25, which is a dedicated board with a accelerator, and Umbrella provides a toolkit, and it's not that easy to work with this toolkit and convert the model, but using a service like this, you can just load the model and execute the operation. It will quantize the model or reduce the representation or the size of the model, and apply lots of other features like layer fusion and other important operations to reduce and optimize the models to run faster on these edge devices. Also, this is the agent, SageMaker Edge Agent, that is running as just a demo there, an application, and you load one or multiple models to expose to the application for the inference. Okay. Another use case, it's similar to the first one, so you have a conveyor belt passing the products, but this is a different in a more restricted scenario, because here the customer needs to take the measurements of the products. The original use case is to predict the measurements of bricks, so clay and concrete bricks. But this is a public data set that we are using just because it has similar shapes, sort of. And we helped this customer to create a custom model. So it's a convolutional neural network, a computer vision model, similar to a pose estimation. The prediction is a regression, and the regression is a set of corners, the corners of the object. So, and then you have a post-processing code that gets these corners and computes the edges and the areas in the surface. This is a super hard problem, especially because you need to have a very a camera position at the right place with focusing at the right angle. If you change anything, you need to recalibrate this. Otherwise, you can increase the error of the measurements of these bricks, right? So for the POC, we achieved very good results. So the accuracy was above 90%, which is great. But again, you need to calibrate and put the camera at the position, at the specific position. Otherwise, you can introduce errors to the measurement. So I said that this is similar to pose estimation because in pose estimation, the corners in this case are the bones of the person that you're trying to estimate the pose. Okay. And then a third scenario is a POC. It's a POC that we created with a customer that works with the components for wind turbines. So it's a toy. We created this 3D printed wind turbine farm. So 5 wind turbines with 5 Jetson Nanos, as you can see there at the right side. And we created an anomaly detection model to get the raw data collected from the turbine, so from vibration, temperature. If you compare to a manufacturing scenario, so you have gearboxes, motors, and similar things. So what we're doing here, we're extracting this information, the raw data, pre-processing and sending it to an anomaly detection model. In this case, it's an autoencoder that will try to reproduce the input. So you give the raw data, of course, the pre-processed raw data to the model, and it tries to reproduce the input at the output, and then you measure the error to see if there is an anomaly. And then this is the reference architecture of this POC. At the bottom, you can see the machine learning pipeline, also automated by SageMaker for the the model training and the model compilation. In this case, New is compiling the model or optimizing the model for Jetson Nano. So a Linux device, ARM CPU, and an NVIDIA device for GPU. So under the hood, it uses TensorRT to optimize the model for the GPU. And then at the edge, you have a Python application reading directly from the USB connection on Arduino. In a real scenario, you will probably read from SCADA or other real mechanism. This is a toy, so it's just a simplification or oversimplified model. And then it detects the anomalies and sends back to the cloud, and then you can see, visualize the anomalies using Elasticsearch and Kibana, the dashboard, to see the anomalies. If nothing happens, it basically ignores the information. This is your decision. You can send back data back to the cloud or not. This is one of the characteristics of machine learning at the edge. So you can have legal restrictions that you can't send data back to the cloud, so you need to process everything at the edge, or the payload is too big to be sent to the cloud, or too intense. In this case, it's too intense to be sent to the cloud. Doesn't make sense, so you process this with machine learning at the edge, and then just send a small payload back to the cloud with the answers. And this is just the specification of the wind turbine. So an MPU, so for the accelerometer to extract the raw data, some rotation encoder to count the rotations per second, and a servo, a hacked servo acting like a generator, voltage generator, and yeah, the Arduino. That's it. Thank you.